most efficient and stable was to use the pseudo-inverse. So iteration as shown by this equation. The other thing is that we need good starting points for the Newton iteration. And we also have the problem that it's actually possible to have more than one solution through a single triangle when you have shading normals. So our solution to both of these is to subdivide the triangle as needed, to isolate the solutions and to make sure that our starting points are close to the roots. We have two different subdivision oracles. The first comes with very strong guarantees, and it's based on Krawczyk's interval extension of Newton's method, and it was also used by Mitchell Hanrahan in their subdivision that is actually necessary. So we also have a fast empirical heuristic based simply on solid angles of the triangle and normal that we found works very well in practice. So the summary for a single triangle, if there's no shading normals, we just use the 1D Newton iteration to solve for P. If there are shading normals, we check the subdivision oracle. If it passes, then we use the 2D Newton. And if it doesn't pass, then we split it into 4 subtriangles and try again. And then once we've actually found a solution, we test to see it's actually inside the triangle. So now move a little on to talk a little about the hierarchical culling. So when you have a complex mesh, most of the triangles will not contain any solutions for P. And so we've come up with 3 quick culling tests to cull out such triangles: spindle, sidedness, and interval. The interval is a fairly straight application of interval mathematics to the equation, so I won't talk about that one more. But the spindle is more interesting. So it's based on the fact that the refraction can only bend the path by a limited angle that depends on the index of refraction, so the arc cosine of 1 over eta. So if we take in 2D the locus of all points that will bend the path by exactly that amount, this forms an arc of a circle. And in 3D we can revolve this into a surface of revolution that we call the spindle. And solutions can only exist inside this spindle. So we can take the triangle and test to see if it has any intersection with the spindle and reject it if it doesn't. And this is a very useful test because it doesn't rely at all on the normal, it's purely on position. The sidedness test relies heavily on the normal. It tests the condition that the light source has to be on the outside of the local surface and the receiver V must be on the inside and within the critical angle. So we can test if the light source is within the yellow region and the receiver is within the blue region, and if it's not, then we can reject that triangle as not having any solutions. Applying culling to individual triangles doesn't actually buy you that much, but when you start to apply it to large groups of triangles, you get large performance gains. So what we actually do is we build up this 60 position normal tree where the leaves are the boundary triangles and each node stores a box and a cone that bounds the positions and normals of all the triangles in its subtree. Then we do a top-down traversal, and each step we check to see if the culling tests can prove that there's no solutions in that subtree, and if so, we can skip all of the triangles in that subtree. So here's an algorithm summary. So we start as a preprocess, we build a position normal tree for each of the boundary meshes. Then for each IRA, we're going to trace it until we find a point that we want to shade. We're going to select a light source point, which could be a point source or a point on an area source. Then we're going to traverse the tree to solve for all P on the boundary, and that's pretty much all the methods I've been talking to up to now. And for each solution, we're going to check for occlusion along the path, compute the effective distance to the light source, and add the contribution. And we have to compute the effective distance to the light source because refraction alters the usual 1 over r squared fall off from a point source. It can both focus or defocus the light. So for triangles without a shading normal, there's a simple analytic formula that's in the paper. For triangles with shading normals, it's a little bit more complex, but you can use the ray differentials method from Iggy's 99 SIGGRAPH paper to compute it, and there's details on that in the paper. So now I'll move on to some results. So here's 3 scenes without shading normals. We have the teapot inside some purple glass. We've got a cube octahedron with volume scattering and the scorpion in amber. And so for 512 by 512 images, 64 samples per pixel, we can compute these in about 14 to 20 seconds on the CPU. Here's a comparison of the teapot comparing against when we ignore refraction versus our method, and you can see that it makes a lot of visual changes in the appearance. You can see the individual beams that are coming through each of the faces of the cube. You can also see that the glossy highlight actually splits into